everybody. Welcome back to Mathematical Statistics. Today is the day we are going to UMVUE, and it stands for Uniformly Minimum Variance Unbiased Estimator, which is the greatest estimator in all the land. So let's talk about this acronym a little bit. Not everyone uses all of these letters. So Uniformly Minimum Variance Unbiased Estimator, I call this an UMVUE, a UMVUE, for obvious reasons. Some people leave off the U and just call it an UMVUE or an UMVUE, and it pretty much sounds the same, but it looks different, but they still mean the same thing. Some people leave off the E because instead of just saying, I'm going to find an UMVUE, they'll say, I'm going to find an UMVUE estimator. So they bring the estimator part into their, language and leave it out of the acronym. But as I said, I call it the UMVUE, and so do a lot of people. So the word uniformly in math means for all. And what is that all? Here. What we want to do is find unbiased estimators of something. So suppose we have a random sample x1 through xn from a distribution with an unknown parameter theta. And for simplicity, let's just say we want to estimate theta, although we're going to find UMVUEs for tau of theta, for functions of theta, like theta squared or the log of theta. But just for now, let's talk about theta. If you find an estimator, you're going to call it theta hat, and maybe this is your common sense estimator, some kind of guess, method of moments, maximum likelihood. I don't know where this comes from, but we've seen many times that we can find multiple estimators for a parameter theta. So suppose we do have a couple of estimators, a theta 1 hat and a theta 2 hat. If they are both unbiased estimators, the next thing we want to look at to figure out which is the better estimator is the variance of each, and we want to compare them because we want something with lower variance. So I do not have an actual problem or distribution here. I am just going to make up a variance. So if you're wondering where this came from, I'm just making this up. We have seen a variance like this many times, a theta squared over n. And as you see, it is a function of the unknown theta. So suppose I compute the variance for my theta 1 hat and my theta 2 hat, and maybe, so n is going to be fixed, and as a function of theta, maybe this is the variance for theta 1 hat, but as a function of theta, maybe this is the variance for theta 2 hat. Which is the better estimator? So the first estimator, the one that's in white here, has lower variance between here and I guess approximately here. And the green estimator or second estimator has lower variance out here. So I would like to use the first estimator if the true theta is in here, and the second estimator if the true theta is in here. But we don't have that luxury. Theta is unknown. That's the entire reason we're estimating it. So I can't tell you which is the better estimator. What we want to do is find another estimator that has minimum or lowest variance uniformly in theta. So the variance graph is not going to look like this, but basically our UMVUE is going to be something that has lower variance for all theta, uniformly in theta, among every single possible unbiased estimator for theta there is. That's what makes it so great. And these do not always exist, and sometimes they are not so easy to find. And a lot of people say, oh, it's great as an academic thing, but if you go into industry, you're never going to use an UMVUE. But I disagree. And I've got some of my own data on that. So you're not going to use it as much as maximum likelihood estimation, but if you can use it, why not? It is great. Okay, so how do we find an UMVUE? There's a very famous theorem that's going to guide us, and it is known as the Lehmann-Scheffé Theorem. And it goes a little something like this. What we have to start off this theorem is we have some data. So we have like an x1 through xn that are probably IID, but I'm going to say more generally with a joint PDF f of the vector x and theta, which could also be vector valued. So probably this comes from multiplying the individual identical PDFs because these are usually IID for us. And we have a target, meaning the thing we want to estimate, which generally is going to be a function of theta. That could be theta itself, but we call that tau of theta. And we're also going to assume we have a statistic, capital S, that is complete and sufficient. So this is what we need to make an UMVUE. So here's the punchline. If you or we can find a function of this complete and sufficient statistic S that is unbiased for our target, tau of theta, then we, or in this case you, have the UMVUE, the Uniformly Minimum Variance Unbiased Estimator. And I did say the and not a because we're going to see that this is a unique thing. If an UMVUE exists, there's only one. And which this reminds me that I have to go back and talk about complete and sufficient statistics a little more, but I don't want to do that right now. I will talk about this in the next lecture. But I just want you to know at this point, or hopefully you'll take my word for it for the time being, that a complete and sufficient statistic is essentially unique. It's not unique, but it's unique up to one-to-one transformations. So I might be using the sum of the x's as my complete and sufficient statistic, and you might be using x bar, but that's just 1 over n times the sum of the x's. If we both have a complete and sufficient statistic, I claim that there's only one, and so even if they don't look identical, there's a one-to-one transformation. From mine, I can get yours, and from yours, I can get mine. And this is, a big thing. We do need to show this, but I'm going to leave this for next time, where I'm going to show a lot of kinds of statements like this, like when you have something that's sufficient and complete or not complete, or when is this unique and when is that unique. We're going to answer a lot of interesting questions next time. But today, I just want to UMVUE. So let's prove the Lehmann-Scheffé theorem. I'm not even going to write this out. We've basically written everything we need, and it's more of a discussion pulling it all together at this point. I have a complete and sufficient statistic S, which is essentially unique. There is a complete and sufficient statistic called S, and I found a function of S that is an unbiased estimator for tau of theta. And I invite you to bring your favorite unbiased estimator for tau of theta and all your friends and neighbors, everyone in this class, everyone online, bring your best unbiased estimator to this competition where we're going to find the uniformly minimum variance unbiased estimator. So I followed the Lehmann-Scheffé theorem. I took this complete and sufficient statistic and manipulated it until I came up with a function that was unbiased for tau of theta. Now you have an estimator, and your estimator is one of two things. It's either a function of S or it's not a function of S. It has to be one of those. So if your estimator is not a function of S, then I will take your estimator, your unbiased estimator, and I will condition on S and compute an expectation. I will Rao-Blackwellize your estimator, and I will get something that is still unbiased for tau of theta and has lower variance. And it really will, because when we proved the Rao-Blackwell theorem, we said that the new variance is going to be less than or equal to the original variance, and the only way it will be equal is if in that Rao-Blackwellization step, you didn't change anything. But once I condition on S, it will be a function of S. And you said yours was not a function of S. So it's definitely a different estimator with a strictly lower variance. When we talked about the Rao-Blackwell theorem, we didn't have completeness yet. So I'm just using sufficiency so far in this argument. So if yours was not a function of S, leave now. And I just want to talk to everyone remaining who has an unbiased estimator for tau of theta that is a function of S. I have one, and you have all your favorite unbiased functions of S that will estimate tau of theta unbiasedly. But here's where completeness comes in. The definition of completeness, weird as it may seem, we saw at the very end of the last class that it guarantees that there is only one function of S that can be unbiased for whatever you're targeting. There can't be multiple functions of S that are unbiased for tau of theta because S is complete. Therefore, you guys that are left with an unbiased estimator for tau of theta that's a function of S, you must have what I have, and I followed the Lehmann-Scheffé theorem. So no one can do any better. I can either Rao-Blackwellize your estimator to get something lower, but if you lower variance, but if you already used a complete and sufficient statistic, we can't do any better. So one more time, I follow the recipe of Lehmann-Scheffé, and first I knock out everyone who brought a biased estimator, because that's just silly. And then everyone who's left has an unbiased estimator, so I knock out everyone whose is not a function of S, because we can Rao-Blackwellize it and make it better. And then everyone else, we high-five each other, we celebrate, we all have the same estimator, we have found the UMVUE. Let's try it. We only have 2 examples so far where we have a complete and sufficient statistic. We've done a lot of sufficient statistics, but not complete and sufficient so much. And showing something is complete is kind of difficult. So let's start off with our known examples. We had the uniform distribution, I think, last time. So suppose I have a random sample, x1 through xn, from the uniform distribution on the interval from 0 to theta. And when you write that, it's assumed that theta is positive because of how we write intervals. And I want us to find, I'm going to have 2 parts here. So let's find the UMVUE for just theta itself. In other words, tau of theta equals theta. I did just talk about this idea that, once we remove the people who have unbiased estimators, it's not a function of S. We all must have the same thing. But I will explicitly prove in the next class that UMVUEs are unique. Okay, so let's just follow the recipe and see what we can do. We have done the hard work so far here. We know a complete and sufficient statistic. I am going to backtrack just a little bit and look at the joint PDF. I'm just going to go straight to it. This was 1 over theta to the n, and then a product of n indicators that each put xi between 0 and theta. And we rewrote this product of indicators a couple of ways. We rewrote it as a product of just 2 indicators, one putting the minimum between 0 and theta, and the other putting the maximum between 0 and theta. But then we realized that we can write this yet again as putting the minimum between 0 and the maximum, as long as the maximum is between 0 and theta. We did all of this when we were looking for a sufficient statistic, and that's where we're trying to break this up into a pure x, or at least non-theta part. So this could be h of x could equal 3. It doesn't have to have x, but it definitely has no theta. And then g of s of x and theta. And this is where the x's and the thetas are mixed, and we go in there and we see how the x's are represented and pull that out. And by the factorization criterion, we have a sufficient statistic. So using this third expression for the joint PDF, I have this as my h of x, my pure x part, and then the rest of it is the g function. And if we go in there and we see how the x's are represented, they're represented through a maximum. So capital S, defined to be the capital X sub n in parentheses, the maximum, is a sufficient statistic. But we also talked about these other factorizations, like up here, where the sufficient statistic would consist of both a min and a max. And in the top line, the sufficient statistic will consist of the entire data set. So if I gave you the n-dimensional statistic, that is capital X1 through capital Xn, that is sufficient as well. But we proved last time that this one is complete. And as a hint for you, because it's hard to show things are complete, so I would hate for you to try to do it on something that's not even complete, you want to go as low as you can in dimension. And we are going to talk about something known as minimal sufficiency, which is not exactly defined in terms of dimension. So please wait on drawing a conclusion about what minimal sufficient statistics are. But just as a hint for you, if you're trying to find something that's both complete and sufficient, you should go for sufficiency with the factorization criterion and reduce dimension as much as possible. And then hopefully you can show it's complete. So I'm not going to show this is complete again. We already saw that this was complete in the last class. So S is both complete and sufficient. We just showed it was sufficient here. And in the last class, we used the definition of completeness, which involved an expectation of a function of G of this. And we don't even need to talk about that right now. So I just claim we showed this in the last class. I'm going to find more complete and sufficient statistics for you today. So we'll get to talk about this again. But according to the Lehmann-Scheffé theorem, we want to find a function of this whose expected value is the target, the thing we want the UMVUE for. We have worked with the maximum for the uniform zero theta distribution several times. The PDF for the maximum is n over theta to the n, x to the n minus 1, and x does need to be between 0 and theta. And as usual, it's perfectly fine if you don't know that. I think we've used it a lot, so maybe you do know that. But if you need to figure out the expectation of the maximum, you need to know its distribution. If you're going for its distribution, you should first go for the cumulative distribution function. And we've done that several times. And you get a result and take the derivative, and we do end up with this. So what is the expected value of the maximum? We have computed this in the past, but I think it's worth doing again. The expected value of the maximum is the integral from minus infinity to infinity of x times the PDF for the maximum with the argument x dx. Using the fact that our indicator is going to cut off the limits of integration here, this is going to be 0 to theta x n over theta to the n x to the n minus 1 dx. This is n over theta to the n, the integral 0 to theta of x to the n dx. When you integrate, you're going to get x to the n plus 1 divided by n plus 1, and you're going to plug in thetas, and you're going to get some cancellation. And in the end, you'll end up with n over n plus 1 theta. And it makes sense that this is less than 1, right? Because we're looking at data and we're trying to figure out what the maximum possible point is. And so when we have a maximum observed, the true maximum allowable value, the theta, is somewhere above that, likely. And so we have something that's below 1, so this makes sense. And we do have something that's going to 1, which means if you had an infinite amount of data, you would eventually push all the way up against that right endpoint. So this is not an unbiased function for theta, but we can easily adjust it. I'm going to make an estimator. I'm going to put a hat on it, and it's going to be n plus 1 over n times the maximum. This is what you need in order to make the expected value theta. This is a complete and sufficient statistic, so we are done. This is the UMVUE, the uniformly minimum variance unbiased estimator for theta by the Lehmann-Scheffé theorem. It's as easy as that. I mean, I cheated. I used a statistic we already showed was complete, but once you have that, it is as easy as that. There's our first UMVUE. In fact, we have seen many UMVUEs so far, and we're gonna, as we do more examples, see a lot of estimators that we've already used or maybe found as MLEs or method of moments or best guess estimators, but now we have some rigor behind it. So for the next example, actually, I said there'd be a part B to the other problem, so let's stay in this example, the uniform example. I'm going to call this part B. Let's find the UMVUE for tau of theta equals theta squared. I just brought this in because I want to make the point that I keep saying that complete and sufficient statistics are for the model. It's not specifically for theta, it's for estimating theta or any function of theta given a particular distribution. Again, if you were to do the factorization criterion, and write out something that's like an h of x and a g of s of x and theta, you could go in there, especially if theta is a positive parameter, so there's no confusion, and replace every theta with the square root of theta squared. And then you have it as a function of theta squared. So it doesn't matter. You don't need to do this, but that's the idea, that if something is sufficient for theta, it's sufficient for theta squared, and the same thing holds for completeness. So I don't think I wrote steps last time, but for step 1, we want to find a complete and sufficient statistic, and we are still working with the same one, even though we've moved to estimating theta squared. That's the statistic that's going to work for any function of theta. And then step 2 is to find an unbiased estimator for our new target for theta squared based on S. I did just remind you what the PDF for the maximum is. S is the maximum, and the expected value was not theta, but it was adjustable to be a theta. So I'm going to try the expected value of S squared. We know this is not going to give us the first expectation squared, but if we try it, we're going to have the integral from 0 to theta of x squared times n over theta to the n, x to the n minus 1 dx. And let's do the integral. Let's see what we get. Let's see if we can salvage this problem. 0 to theta, x to the n plus 1 dx. When we integrate, we'll get x to the n plus 2 over n plus 2, and we'll plug in the theta, and we'll actually have some cancellation, but 2 thetas left. We'll get n over n plus 2 theta squared. But we want to see just theta squared. So for some notation, tau of theta was theta squared, and the UMVUE for this tau of theta, which is theta squared, is tau of theta hat, and I'm going to define it so that I get theta squared here. So remember, S was the maximum, so I'm going to flip this coefficient to the left-hand side and take n plus 2 over n s squared. And S was the maximum, so this is going to be n plus 2 over n times the maximum squared. This is a function of our complete and sufficient statistic, which was the maximum, and this function is unbiased for theta squared, so it is the UMVUE. We're done. It's just that easy, although I am conveniently skipping over the fact that showing completeness is not easy, but I have some tips for you today. So the second example that we talked about last time, we found a complete and sufficient statistic, so I want to use that to find another UMVUE. We looked at the Bernoulli distribution. We had an x1 through xn IID from the Bernoulli distribution with parameter p. Okay, and we found that a complete and sufficient statistic for p was the sum of the x's. We found this by using the factorization criterion to get something sufficient, and then we went through the difficult definition of completeness to show it was complete. So I want to take advantage of that to find the UMVUE for, let's make this one nice and simple, tau of p equals p. Okay. Step 1 is find a complete and sufficient statistic, and this one's already done. We did it last time. It was the sum as I goes from 1 to n of the xi. If you want to say it's x bar, that's okay. Simple, or even not simple, but one-to-one transformations of this are still complete and sufficient. And Again, this is from last time. After this example, I promise to do a bunch of new examples where we find that things are complete in a much easier way, because that was quite a bit of work. But let's just go right on to step 2. We want to find a function of s whose expected value is p. In other words, a function of s that is an unbiased estimator of p. What do we usually do in a situation like this? We start with the statistic. Let's look at the expected value of s. This is the expected value of the sum as I goes from 1 to n of the xi. You have two options here. One is to recognize that the sum of Bernoulli's, IID Bernoulli's, has a binomial distribution with parameters n and p, and the mean or expected value of the binomial is n times p. But if you don't remember all those details, we can do the, nice linear operator here, and the fact that these are IID, so by the identicalness of the distributions, identical, this is going to be n times the expected value of one of them. And then you can compute or recall or look in your table. The expected value for the Bernoulli random variable with parameter p is p. So again, if you didn't want to do all that and just recognize that this has a binomial distribution, by all means, go for it. This is not quite p, but this is a function of s whose expected value is pretty close. So we just need to adjust this. So my p hat is going to be 1 over n times s, which is 1 over n times the sum of the x's, which is x bar, is the uniformly minimum variance unbiased estimator for p by or using the Lehmann-Scheffé theorem. We've already found unbiased estimators for the Bernoulli and got x bar in the past, so we've already seen many UMVUEs, but we didn't know it at the time. So, completeness, hard to show. Hard to even know what to start with. I did give you a hint that if you find a sufficient statistic using the factorization criterion, you want to go as low as you can in the dimension if you want any hope for it to be complete. But I do have a kind of factorization criterion that pops out something that is both complete and sufficient, which is awesome because we don't like to show completeness. So I have a definition for you. I want to talk about things known as exponential families. These are families of PDFs, probability density functions, that have a certain form. I have two definitions for you. One is so the first one is going to be when the parameter is one-dimensional. So I'm going to start this off with x1 through xn come from a one-parameter exponential family if, number one, theta is only one parameter. So I'm going to say theta is one-dimensional and not actually a vector containing more than one parameter. And two, the joint PDF can be factored in a certain way that's different than the factorization criterion. So f of the vector x and the one-dimensional parameter theta, we need to be able to write this in this form as some function a of theta only times some function b of the x's only, or, any one of these could be, not any one of them, I'll say something about that, but these could be constants in theta and in x, but you can't have any x's over here and you can't have any thetas over here, times e raised to the c of theta times d of x. I'm going to be super lazy here and just write some dots, meaning 4 appropriate choices of A, B, C, and D. The only thing you need out of them is for them to make sense. For example, if A of theta or B of x is 0, this couldn't possibly be a PDF. If A of theta was negative, then B of x had also better be negative, or you'd get a negative PDF. We can't have one of these functions, C or D, be 0, because then we wouldn't have that exponential in there and we wouldn't have the right form. So the ... I could say for A times B positive, and but things that make sense, that make it a valid PDF. If it can be factored in this way, we say that the data comes from a one-parameter exponential family. And if it comes from a one-parameter exponential family, then this is a kind of factorization that pops out a complete and sufficient statistic. So I'm going to put a little squiggly line here. I want to continue this thought, but I am done with the definition of one-parameter exponential family. So I'll put like a star here, a little claim. If x1 through xn come from a one-parameter exponential family, the statistic capital S defined to be this function D with the capital X's plugged in is a complete and sufficient statistic. Unfortunately, I don't have time to prove this. It's not pleasant. It's not bad for a discrete distribution. It's not the most pleasant thing. I would promise to write it up for you and post it on the Canvas page, but I'm getting pretty behind on my promises, so I'm not going to make any promises here, but that is my plan. So I'm going to ask you to believe this claim. Just like with the factorization criterion, you could factor this a little differently, especially when it comes to constants. So if you take, like, maybe your d of x was the sum of the x's, or maybe it was 1 over n times the sum of the x's, or maybe you put that 1 over n over here. Whatever you get is going to be essentially what I get up to one-to-one transformations. So that is that uniqueness of the complete and sufficient statistic. So don't worry about where all the constants go, but you generally want this to be as simple as possible, because that's what we're going to start with and try to guess an unbiased estimator for the target. So before using this wonderfully useful and convenient exponential family factorization criterion, I do want to give you the definition for when your theta parameter is 2-dimensional or 3-dimensional or something like that. So as another definition, x1 through xn come from a k parameter exponential family. You're really guilty using abbreviations in a definition, but similar to the last definition. So when it's your first time seeing this, I should probably write everything out more cleanly. But it comes from a k parameter exponential family if, number one, the parameter we're talking about is k-dimensional, like 2-dimensional alpha and beta for the gamma distribution. And number two, the joint PDF can be written, so it'll have its own exponential family factorization. F of the vector x and theta is going to be some a of theta, some b of x, and then e to the sum as I goes from 1 to k of ci of theta di of x. If you can do this, you have a one-parameter exponential family, and then you can peel out sufficient statistics. So here is the claim. The statistic S, made up of the k components, the d1 of x, d2 of x, out through dk of x. This is a vector of k complete and sufficient statistics, or a k-dimensional complete and sufficient statistic. One thing I need to point out here is that nowhere in this line do you see a theta sub I. So if you have two parameters like mu and sigma squared, or alpha and beta, you are not required to pull this apart into an alpha part and a beta part. Not at all. There's no ci theta I. again, you don't see the components of the theta written in there. So I think this will become clear when we do an example. Let's get going. Let's get going. Let's start with a one-dimensional example. So, and something you might be thinking right now is, well, how often do we have an exponential family? I know the exponential distribution has an E in it, and the normal distribution has an E in it, and gamma, but we can make a lot of things into this form by putting a log and an E. So it might not look like an exponential family at first, but it's going to be in a lot of cases. So for this example, let's let x1 through xn be IID from the continuous Pareto distribution with parameter gamma, and gamma has to be positive. That's the parameter space. Let's find the UMVUE for gamma. So that's our tau of gamma equals gamma. Step one is going to be to find a complete and sufficient statistic. And now we have some work to do, but it's not as bad as the work we did in the last lecture. I should write A. This is unique, but up to one-to-one transformation. So find a complete and sufficient statistic. I just had this exponential family definition, so probably that's what I'm going to use. The PDF for one of these, oops, not going for the joint yet, is gamma over 1 plus x to the gamma plus 1. And just like it was true for the factorization criterion for sufficiency and for factorization to show things are independent, whenever you have something that says your PDF needs to factor into an x part and a theta part, you do need to include the indicators. You need those to be able to separate as well. So I'm going to make sure I have my indicator that says that x is between 0 and infinity. I can tell you right now that if your parameter is in the indicator, there's going to be no separating it. Unless maybe way back at the beginning of the course, we talked about twisted indicators where things looked really hopeless and combined, but we were able to tease it out. But for the distributions whose support depends on the unknown parameter, like the uniform distribution, the exponential family factorization is not going to work. Okay, so the joint PDF. I'm going to put a vector over this. And because these are IID, I'm going to take the product as I goes from 1 to n of the f of x sub I and gamma. And I'm going to plug this in, and I'm just going to go straight to the answer. We'll get gamma to the n, the product as I goes from 1 to n of 1 plus xi, all raised to the gamma plus 1. Or you could have that exponent on each term in that product, but just like we've seen in the past, we kind of are trying to pull things apart. So let's bring that exponent out. And a product as I goes from 1 to n of this indicator evaluated at x sub I. Right now, I'm looking for A of theta, which is pure parameter stuff, and then a B of x, which is pure x stuff, and then E with some other stuff. So pure parameter right here. We don't have a theta in this problem, but this is going to be, let's stick this out front. This is going to be A of gamma, or write a theta if you want, but that's pure parameter stuff. And this looks like pure data stuff. So I'm going to put this out front here. You don't have to actually reorder things. I'm just going to do it for our first few times looking at this. This is going to be my B of x. I could also choose to take this one power of all this stuff out and make that part of my B of x, but it's not really going to matter. What I'm left with is, so I'm not finished, but I've got this product as I goes from 1 to n of 1 plus xi in the denominator. So let's write that as this with a negative exponent. I'm going to put an E and a log on that. And that will make the rest of this PDF. Once we bring down the exponent, we're going to have E to the negative gamma plus 1, and then the log of the product, which I'm going to write as the sum of the logs. If you write it as the log of the product, that's fine. But in step 2 of finding the UMVUE, you're probably going to write it as the sum of the logs. So you see there was no E, and now there's an E. And this looks like it's going to be our C of theta, in this case gamma, and this a D of X. And if you pulled the negative into the D of X, that's fine too. And if you multiplied this out and pulled out the stuff without the gammas way out here, that's also okay. But we can say by one parameter exponential family, the statistic S, which is D of the capital X's, which is the sum as I goes from 1 to n of the log of 1 plus xi, is complete and sufficient for this model. So that is the end of step 1, finding a complete and sufficient statistic. Let's go to step 2. We're still trying to get an UMVUE for the gamma parameter. I want to find a function of S that is unbiased for gamma, or whose expected value is gamma. Again, if you had like maybe a 1 over n up here, and then like you put like an n over with the other part, you might have a slightly different statistic, but we're both going to take the expectation and adjust until it's unbiased. And we're going to end up adjusting differently, but ultimately we'll get the same thing in the end. I might end up having to include a 1 over n at the end, or you might have to end up removing it by multiplying by n. In the end, though, the UMVUEs will be the same. We have looked at this log thing way back, maybe in the first week of the semester. In order to find the expected value, we have a couple of options here. I'm going to look at, as usual, the expected value of S itself. And I could bring the sum out and look at the expected value of the log of 1 plus xi. And I could say that because they are identically distributed, this is n times the expected value of the log of 1 plus x1. How to find that expectation? You could do this by definition, because this is actually integrable. I'm not going to do it because I want to keep us to the lowest set of integrals we need to know to get through this. But there is a substitution that you could make where this is not that bad. But I'd prefer not to. Let's find the distribution, if we don't remember it, of the log of 1 plus x, where x has a Pareto distribution. So x is just a generic x. Call it x1 if you want. This is like a y equals g of x equals the log of 1 plus x. And I want to find its distribution, so we want to invert this. X is g inverse of y. And this is going to be e to the y minus 1. So the PDF for y, been a while, but this is the PDF for x with g inverse y plugged in, times the absolute value of the derivative with respect to y of g inverse of y. And our f of x was the gamma over 1 plus x to the gamma plus 1 and an indicator. So let's go. Gamma over 1 plus. Now in for that x, I'm going to put the e to the y minus 1. This all gets raised to the gamma plus 1. An indicator that says that e to the y minus 1 has to be between 0 and infinity. And then I do want to put on the absolute value of the derivative of this with respect to y. So this is the absolute value of e to the y. But e to the y is always positive, even if you plug in a negative, so we can drop the absolute values. If you subtract the 1, add the 1, and subtract the 1, you've got an e to the y down here in the denominator raised to the gamma plus 1. So if you multiply the exponents, you have an e to the gamma y plus y down in the denominator. And with this e to the y, this will cancel. So we have gamma over e to the gamma y, and then an indicator. So where does y live? If e to the y minus 1 is between 0 and infinity, then you could add the 1 all the way across, and this is still infinity. And then you can take the log all the way across, and you get 0 less than y, and the log of infinity is infinity. So that's our new indicator. Our y values can go from 0 to infinity. Look like something you know? Yeah, write it this way. Gamma e to the negative gamma y times this indicator. We have just shown that if you start with a Pareto, this function, or let's go back here, the log of 1 plus the Pareto has an exponential distribution with parameter lowercase gamma. So I could use that to find the expectation of this, or I can even use it all the way back here. We've got S equals the sum as I goes from 1 to n of the log of 1 plus xi. And these guys are IID exponential with rate gamma. And that means the entire S has a capital gamma distribution with parameters n and little gamma. So let's find the expectation this way. The expected value for the gamma distribution is our alpha over beta parameters using the parameterization we use in this class. So this is going to be n over gamma. Ugh. Ugh. Not good. Remember at the not the very beginning, like the first month of the course when we were trying to find unbiased estimators, things like this happen. We want to get gamma. And if we got like n gamma or 1 over n gamma, we could move the n or the 1 over the n to the other side. But we're kind of in trouble here because the gamma is in the denominator. So this is a problem. So now I do think it's a good idea that we found the distribution of S. Let's try the expected value of 1 over S. You might remember what this is from way back, but because this has a gamma distribution, this is going to be the integral from 0 to infinity of 1 over S times the gamma PDF, 1 over gamma of n, lowercase gamma to the n, s to the n minus 1, e to the negative gamma s ds. If we combine these, and let's pull out some constants. Actually, I'm going to do this all at once because I'm kind of rushing here. This is, you know what, let me not do it. This is 1 over gamma n, lowercase gamma to the n, s to the n minus 2, e to the minus gamma s ds. And this is kind of looking like, remember this? It's been a while. A gamma distribution PDF with parameters n minus 1 and lowercase gamma PDF. So we're going to integrate without integrating. I'm going to make this integral 1 over gamma of n minus 1, lowercase gamma to the n minus 1, s to the n minus 2, e to the minus gamma s ds, because that is that PDF, and I know it integrates to 1. And then let's adjust it so that it actually equals the line above. I'm going to need another gamma out here, and a capital gamma n minus 1 over a capital gamma of n, and then all of this is 1. And then we can cancel here because these are integers. We can write this numerator and denominator as factorials, or we can recall that gamma of alpha is alpha minus 1 times gamma of alpha minus 1. And if we do that sort of thing with this denominator, we will get cancellation, and we have 1 over n minus 1 gamma. So this was the expected value of 1 over s. Oops, try to circle. And this is good news because gamma is, on the line there. It's not in the denominator. So S was the sum of the logs of the 1 plus xi, and we knew that that was complete and sufficient by the exponential family factorization. And we found a function of S that it's almost unbiased for gamma, but we need to adjust it. So we know our final answer is the UMVUE or gamma is gamma hat equals n minus 1 over s, or n minus 1 over the sum as I goes from 1 to n of the log of 1 plus, sorry, 1 plus the xi by the Lehmann-Scheffé theorem. That was a lot more work, but it's still the same simple 2 steps. Step 1 for an UMVUE is to find a complete and sufficient statistic. And we've now got this exponential family factorization trick, which works even if there's no E in the problem a lot of the time. Sometimes it won't. And then step 2, we want to play around with that statistic and find a function of it that is unbiased for our target, in this case, lowercase gamma. And yeah, we pulled together a lot of skills from the entire semester, but we did it. This is the UMVUE. And now we're getting, some things that do not look entirely guessable, right? This isn't what you'd get out of, say, method of moments. It doesn't appear to be obvious, but it is unbiased and has uniformly the smallest variance, uniformly in lowercase gamma among all unbiased estimators. It is the greatest estimator for the gamma parameter of the Pareto in all the land. Okay, in the remaining time, and maybe I can get a little further than this, I want to do a 2-parameter example. So suppose I have x1 through xn, IID, normal, mu, and sigma squared. Now, if I say where mu is known or where sigma squared is known, then it's a 1-parameter problem, but I'm not going to assume either one is known. Let's find UMVUEs for mu and sigma squared. Step 1 is going to be to find a complete and sufficient statistic. And I'm going to try the factorization, the exponential family factorization. So the PDF for this normal is 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x minus mu squared, and we generally don't write an indicator because it would go from minus infinity to infinity, so it's 1 everywhere. But the important thing is that it does not involve the unknown parameters. The joint PDF we get by multiplying a bunch of these out. We're going to get the 2 pi sigma squared to the 1/2 power n times and in the denominator. So I'm going to write this as 2 pi sigma squared to the minus n over 2, and then e. You don't have to write it with that exp. You could just leave it like this. Minus 1 over 2 sigma squared, the sum of the xi minus mu squared. Okay, so what do we have here? This looks like pure parameter part, but this involves the parameter and x. If I had said that mu was known and sigma squared was the only unknown thing, you could have this be your statistic. It can't involve unknown parameters though. So let's massage this a little bit more. I am going to do this not live, I guess. I'm going to square this and run the sum through and run this through and do a factorization all at the same time, just because I'm running a little bit late here. So I've got 2 pi sigma squared to the minus n over 2. And I have, actually, I'll give it 2 lines. This is e to the minus 1 over 2 sigma squared times the sum of the xi squared. Then we get minus 2 mu, the sum of the xi, but we get some cancellation. I get plus mu over sigma squared, the sum of the xi. And then finally, I get n mu squared with the negative stuff in the front. So I get negative n mu squared over 2 sigma squared. So now let's pull this apart. This is, e to this times e to this times e to this. But in the spirit of getting it into the exponential family factorization form, I really just want to get rid of this because this is going to be like the C1 of theta, and theta is mu and sigma squared. And this is going to be the C2 of theta and the D1 and the D2. So let's get rid of this part. I'm going to write this as 2 pi sigma squared to the minus n over 2 e to the negative n mu squared over 2 sigma squared, and then e to the rest of it. I just copy and paste here. This never works out. I have scribbles everywhere. But that's what's going to be in the exponent. And so we want to look for pure parameter part, which all of this is. If you want, you can separate out the 2 pi to the negative n over 2, and you can make that the non-parameter part. That could be your b of x, but it's constant in x. I'm just going to leave it there, and I'm going to call all of this a of theta, but theta is mu and sigma squared. So here's a function of mu and sigma squared, but no data, no x stuff. And then there doesn't appear to be just x stuff. So I'm going to say that the b of x part is identically 1. Or again, I could have brought the 2 pi over into the b function. Over here, I'm looking for a c1 of theta and a d1 of x plus a c2 of theta and a d2 of x. Remember, we're not trying to get the mu for one of them and the sigma squared for the other. In general, each one is going to be a function of the entire parameter vector, although it didn't happen over here. But we take our d1 and d2 and we say by one parameter exponential family, the statistic S, which consists of d1 of capital X and d2 of capital X, which is the sum. I don't know why I'm writing bigger and bigger. This is just that exciting. The sum of the xi squareds and the sum of the xi. This vector statistic is complete and sufficient for this normal distribution where both parameters are unknown. So I'll just say for the model. It doesn't matter if you had these reversed. And you could also just list them separately and say, here is a pair of complete and sufficient statistics, but I'm calling it a vector valued statistic. That's the end of step 1. We found a complete and sufficient statistic. And if you have 2 unknown parameters, you likely have 2 statistics. I can't guarantee that you're not going to have some weird cancellation where you might end up with only 1 statistic or possibly 3, but generally the number of statistics you get is the number of unknown parameters. Let's finish this up. Step 2 is to find a function of 2 functions of these that give you expected value of mu or sigma squared. So find a function of that S, or I'm just going to write out the statistics, and the sum of the xi whose expected value is mu, and this is a horrible sentence, one whose, another function, expected value is sigma squared. We already know the answers here. Mu hat is going to be x bar. You know, that's 1 over n, the sum of the x's. That is a function of this entire vector. It's just constant in one of the components. Doesn't matter that we didn't use both of them. And then sigma squared is going to be our s squared. You know why? Because we don't use it a lot in here, but in a more data-oriented course, you very likely have rewritten your denominator by squaring things and running the sum through, and you'll get the sum of the xi each individually squared minus the sum of the xi all squared over n minus 1, and this clearly is a function of these 2 statistics. So we found a function of this and this, whose expected value give us the mu and the sigma squared. I need a hat over here for sure. And we're done. The UMVUEs. We already found these UMVUEs months ago. But now we know that no one can do any better in terms of unbiasedness and lowest possible variance uniformly, regardless of what the values the unknown parameters take on. Okay, I am out of time almost. I just wanted to say that I basically invited you not to come back for next time because we were going to do some sort of optional fun stuff if you're into more theoretical stuff. But I take that back because I didn't get as far as I meant to today. So I do want to start off with some examples. So if you choose to skip class, make sure you watch the video, at least the first 20 minutes. Um, or maybe I'll see you there. And if not, I'll see you next time on mathematical statistics.